So here's Honor. He's gonna talk about MPT.
Hi, it's Onur. Thank you for having me here. I will be talking about non-native arithmetic in circuits. I tried to prepare some slides, but in the end it turned out to be something like a guide, and I will walk through this document. Equations here might not be so accurate. My goal is to give some intuition how it is done. We have two fields. One is native and other one is wrong. Native field where we constrain equations in circuit, and wrong field is a which is not equal to the native field. I couldn't find how I can do that.
If we can't figure it out fast, then.
Top right corner, the triangle, I think.
Triangle? Wait, I don't know. That's not a triangle. I don't know how to do this either. Whose laptop is this?
Okay.
Okay. Better?
So there are some applications that we use this wrong field arithmetic. One of them might be aggregation or recursion of the same circuit. This is where there's a multiplication. A plus the a multiplies the point x and y, and x and y is in base field, which we call wrong field here. This is a scalar multiplication. And the other example might be the ECDSA. And with the ECDSA, we use that curve, sec P 256. And in that curve, scalar field also is non-native. So in the recursion side, we have the scalar in the native field. So for that purpose, we built some stack that uses Halo2 as a backend. In that stack, we support the original, the ZK Halo2, which uses the IPA commitments, and our fork, it's applied ZKP/Halo2 and supports KZG commitments. So our stack looks like this. On top of Halo2, we have a main gate that implements a standard like Blanc gate with additions, multiplications, and stuff. On top of that, we have integer, big integer crate. On top of that, finally, we have ECC. So with that stack, we can implement recursion or ECC circuits. So other implementations are we mostly follow the Aztec spec. Aztec spec is also implemented in Barentenberg, and MetalLabs also very similar implementation. Also, Scroll has other independent implementation of big integer arithmetic. So our main gate is looks like this. It might not be the best way to represent a gate, but I hope this is familiar to you. We have 5 witness columns, A, B, C, D, and E, and 2 multiplication gates here, and we have one further rotation. And in the end, there's a constant fixed column. So we have a 5-bit gate because it is good for ranging 4 limbs, which we often use, and further rotation is used for running sums. And the 2 multiplication in a gate is good for applying conditional selections in a single row. So main gate also implements this basic arithmetic conditionals, assignments, and equalities between witnesses. We also want this gate to be feasible to verify on-chain, because this gate will be the where we implement recursion stuff, and this gate will be verified in layer 1 contract. So let me zoom out a bit. This is how we represent integers. In this example, where we see 4 limp representation. First of them are B bits, and last one, the most significant one, a bit shorter than the others. So we also have another special limp that holds the native value, which is a combination of these limps under the native field. So we will need this native value in multiplication process. Also in synthesis time, when we synthesizing this circuit, we want to keep the maximum value, this integer might be, to defer some reductions. So we apply reductions when this integer goes beyond some specific limit. So when we assign new witness integers, we range these limps first to be B bits, and last one must be B most bits. And then we also constrain the native value under native modulus. This is trivial to compute because it is under the native field. So we also in synthesis time, maximum value will be assigned to 2 to the power m, which is the next power of 2 of native value. For example, we have native field. For example, we have 11 for the native field modulus, and then this value should be 16 minus 1. Right? 16 is the next power of 2, this modulus. So how we range these integers when we are assigning? As we said, we have 2 columns, witness columns. We just split a limp into sublimbs. In our implementation, a limp is 68-bit here, and B most will be 18. But in the sublimbs, we divide this integer into 4 sublimbs. Will be each of them will be 18 bits. So we just combine them together and see if it's equal to the actual limp. And we also range A, B, C, D, these 4 columns to be in this specific limit. For the most significant bit, we have a special range for B column, which also ranges the overflow, which is shorter than the actual table. So we also combine them to see if it is equal to the E, column A. So addition is pretty straightforward. We just add limps together and don't apply reduction until it's strictly necessary, until it's go beyond some limit. And in the synthesis time, we also track the maximum value of the new witness. Subtraction, if we apply subtraction in a way that we applied addition, these resulting limps probably underflow. So we want to stay above 0, If this underflow, it can be a pretty big number, just less than modulus. To avoid underflow, we pick an auxiliary value and add to the E beforehand. This auxiliary value must equal to the wrong modulus, non-native modulus, but it should also move left-hand side operand, the left-hand side operand above B. How we can do that? Because we tracked what maximum value B right-hand side can be, and we pick an auxiliary value. This auxiliary value will be constant and can take place in a fixed column. So these auxiliary will be assigned in synthesis time. Multiplication will be a bit trickier, but in the end we want to satisfy this equation. Two operands and the right-hand side quotient, and remainder will be our new witnesses. And as they are new, they will be assigned, and they must be subjected to range checks. We will constrain this equation in two fields or rings. First one will be under native field, which is pretty straightforward and a single row equation. We keep all integers native value just after this limp, so we can just compute or constrain this stuff pretty straightforward. So we will also do this thing under modulo T. What is T? T is the for example will show it better. Let's say our limbs are 68-bit sized. Let's say we have 4 limbs. Then T will be 2 to the power 272. Okay, this number also should be larger than our other two fields. Why we are doing this second stuff, modulo T stuff? Because we were about to use Chinese remainder theorem. So if our goal is that if two equation holds in a different modulo, so it must imply that same equation must also hold in wrong field modulus. But in some certain conditions, say we constrain these two equations to be 0, that holds in a T and native. So this problem has a solution in a key multiplies native and T. So we want K to be 0 also. If not, left-hand side equation A and B, and the right-hand side might wrap n times T. Then it would be some soundness errors because prover can find another values that actually not holds this equation, but with some valid witnesses, quotient and remainder. So we need to arrange these guys accordingly. Remainder will be a next integer that we will be using, so it should be arranged as usual, which is the next power of the wrong modulus. And quotient should be in this range. So the right-hand side should hold this equation. It means it should not wrap n times T. So we find the maximum value for the quotient. So range this quotient accordingly. So we also want these two operands, maximum value of them should be less than right-hand side, because if not, even if this guy less than n times t, if this left-hand side, maximum value of this hand side exceeds the right-hand side, so we couldn't find some valid witnesses, so there might be some completeness errors. One thing before we start multiplication constraints, we need to check if operands are under maximum operand possible value. If they likely exceed, so we want to apply reduction just before the multiplication. Reduction is also very is actually very similar with multiplication, but some simplifications. Quotient, we keep quotient as single limb. Okay. So quotient is not a big integer, just for example 68-bit number. So yes, this is the simplified equation, which is very similar with multiplication. Equality, we said the value can exceed the modulus because we range it with next power of 2 of the wrong field modulus. So if we need to really check this value should be under wrong field, we should be in a field, so we have a assert less than modulus constraint, so it can be used when we compare with some value comes from public inputs. I think that's all, and there is some appendix here about this mod T constraints. If you want to look at, link is here in Thank you.
Any questions for Honor?
Forward. Okay.
So you presented ways to do additions, subtractions, and multiplications. Do you do like other operations or?
Yes, we support division and inversion. Actually, they are how we do in the native field. Just check if multiplication is 1. Yes, but in the base we use, for example, multiplication. This multiplication constraint to make division.
Thank you. Okay, thank you, Honor.